All right, now let's take a look at angular momentum. So what we have here is there's a turntable or a large disk or something like that, and there is a lady standing on it over here, standing on the edge, and her mass of the woman is 50 kilograms, and this disk is rotating around with an angular speed of 1/2 revolution per second, so omega is equal to 0.5 revolutions per second. And the mass of the disk this is 110 kilograms. The radius of the disk, this is 4 meters. So we have 4 meters here, like that, all the way out to the edge. So she's actually out at 4 meters as well, right? So she's over there at 4 meters, and kilograms, and we want to know what is the magnitude of the total angular momentum of the woman plus disk system. So two things here. So basically we can just calculate, the momentum of one thing, just like we did with linear momentum. The momentum of the system is the sum of individual momentums. So we can find the momentum of the disk, the angular momentum of the disk, and the angular momentum of the woman, and we can add them together. So here, find momentum total. So angular momentum is L. So we're looking for L total of the whole system, and the solution to this is that the total angular momentum, L total, is equal to the angular momentum of the woman plus the angular momentum of the disk. And actually, angular momentum is a vector quantity, right? Because angular momentum, L, is equal to I omega, right? Just like we had linear momentum. Remember that linear momentum was mass times velocity, right? Linear velocity, and that was the direction of the linear momentum was the direction of the linear velocity. Same thing with the angular momentum. The direction of the angular momentum is the same as the direction of the angular velocity. So we can just calculate this out. We can say that all right, we have L total. The total angular momentum is going to then be the rotational inertia of the woman times the angular velocity of the woman plus the rotational inertia of the disk times the angular velocity of the disk, right? And I'm assuming this is going counterclockwise. They actually just they didn't tell us if it was rotating clockwise or counterclockwise, but they ask us just to find the magnitude of the angular momentum anyway. So if we're looking for the magnitude of it, we'll just treat all these angular velocities as positives. And so then we'll just get rid of this and just look at the magnitude only, because that's what they're asking us for. Okay, then the rotational inertia of the woman, well, we need to find out what this is, right? And so this is her rotational inertia relative to this axis that goes to the center, right? And if we can treat her as a point mass, if we can treat the woman as a point mass, then we go back to the definition of rotational inertia, and the definition of I is the sum of all the masses times their distance from the axis of rotation squared. So if she's a point mass, then all of her masses at one point, there's just one mass and at one distance, right? So we don't even need to sum this up really, because there's just one of them. So it would be her mass times the distance that she is from the axis, which happens to be the radius of the disk, squared. Okay? And then the disk, they tell us is a large disk. Looks like it's a solid disk. So the rotational inertia of the disk would be, this is I woman, and I disk is going to be 1/2 mr squared. And this is just from the table of moments of inertia or rotational inertias that we have, right? And so we have the magnitude of the total angular momentum. This is equal to the mass of the woman times the radius of the woman squared times the angular momentum of the woman, plus 1/2 mass of the disk, radius of the disk squared times rotational velocity of the disk, right? So actually I can factor this out because they're rotating together. The woman is on the disk, right? And so they have the same rotational velocity of 1/2 revolution per second. Right, so I can actually factor out this omega. So let's say here omega of the woman is equal to omega of the disk, which I'll just call omega, which is 0.5 revolutions per second. But let's put this in radians per second. And so this is equal to this comes out to pi radians per second. Okay, so then the total angular momentum is factoring out this omega. I'll write it out here. Omega times mass of the woman times, and actually, let me just, I'll leave it. I was going to factor out this r since they're actually the same r, but we'll leave it in here for now. So r woman, this is the distance the woman is from the axis of rotation squared, plus 1/2 mass of the disk, radius of the disk squared, and we can just plug everything in from here. So the total angular momentum is equal to pi times the woman's mass was 110 kilograms, and then she is 4 meters from the axis of rotation, plus the mass of the disk. I apologize. The woman had a mass of 50 kilograms. The disk had a mass of 110 kilograms. And then the radius of the disk is also 4 meters. And so this total angular momentum comes out to 5.28 times 10 to the third kilogram meters squared per second. Kind of funky units there for angular momentum. We don't have anything special that we call out. It's just kilogram meters squared per second, units of angular momentum. So pretty straightforward. Just like we looked at linear momentum, the angular momentum of a system is the sum of individual angular momentums. Just to kind of expand on this a little bit, if I had one thing rotating counterclockwise and another thing rotating clockwise, then these would actually go against each other. If I had this has a magnitude omega, this has a magnitude omega, and this, whatever this thing is rotating here, has a rotational inertia of I, and this one also has a rotational inertia of I, then this angular momentum of the whole system would be equal to 0, because this would be a positive and this would be a negative. So they add up as vectors, but we're just looking for the magnitude of it, so we just consider them both to be they were both rotating in the same direction since the woman was on the disk, but we didn't care whether or not it was positive or negative.